Welcome back. In this video, we are going to cover section 1.1 about the definition of a metric space and examples of metric spaces and balls in a metric space. Okay. So there are actually 6 sections in this chapter. It's the lengthiest chapter in the course because it contains a lot of concepts and jargon and examples. But we'll proceed slowly. Okay. So what is a distance? Okay, let us start with the usual Euclidean distance between 2 points in the plane, where we have an orthonormal coordinate system. So we identify the plane, the usual plane, with R2, the set of couples of real numbers, x1, x2, or xy. If we have 2 points of coordinates x1, x2, and y1, y2, the usual distance between x and y, as you know, is the radical, the square root of x1 minus y1. First coordinate minus first coordinate square plus second coordinate minus second coordinate square. So this is by Pythagoras theorem. Okay, so this is the usual distance that you know from high school. Okay, let us try to write down the most trivial properties of this distance. What does it satisfy? Okay, the first trivial property is that this is something, it's the real number which is non-negative. Okay, so first thing, the distance is always something bigger or equal than 0. Now, when is it equal to 0? It's equal to 0 precisely when the 2 points coincide. Okay, and the third property, which is also trivial, is that it's symmetric. The distance is a function which is symmetric. So the distance between x and y is the same as the distance between y and x. Okay. Why? Because here you can put y1 minus x1 instead of x1 minus y1 because it's a square. Same thing here. And the most important property is what we call the triangle inequality. Okay. If we have a triangle of vertices x, y, z, then the distance between x and z is less or equal than the distance from x to y plus the distance from y to z. Okay. Now we could have equality. This happens when y lies between x and z. Okay, so this is not always a strict inequality. Okay. Now these trivial properties of the Euclidean distance are now taken as an axiomatic definition in order to go towards more generality. Okay, so in general, a distance on an arbitrary set is what? Is a function of 2 variables. Okay, so it's a function from the product of x times itself into r. Okay, that satisfies 4 properties. Okay, so first thing, it's non-negative, so bigger or equal to 0. It's 0 if and only if the 2 points coincide. It's symmetric, and it satisfies the triangle inequality. Okay, so this constitutes a broad generalization of Euclidean spaces. Okay, we can work on any set actually, not just R2 or R3 or even Rn. Okay, so, and I will give examples now where the set can really be anything. Okay, so it's very general. And a metric space is just a set equipped with a special distance. Okay, now a distance is sometimes also called a metric. Distance or metric, same thing. So a metric space can be thought either as a couple, X, a set with a distance, or a set equipped with a distance, same thing. Okay. And now, as usual, let us give examples of metric spaces. We start with the trivial example, the usual distance on R. Okay, So we take x equal r here, the real line, and we set dxy equal to the absolute value of x minus y, and this is called the usual or standard distance on r. Okay, so you know that it satisfies all these properties. It's trivial. Now, less trivial, another example. I put rho of xy to be the absolute value of x cubed minus y cubed. Okay, this is not the standard, this is something different. Okay, does it satisfy these four properties? Yes, this is what we shall prove now. So first property is trivial. Now, the distances or metrics can be denoted by d, rho, gamma, alpha, anything you like. Okay, d bar, d1, d2. Okay. So first property is trivial because it's an absolute value, so non-negative. It is 0 precisely when x cubed minus y cubed in absolute value is 0, and this happens if and only if x equal to y, because when x cubed minus y cubed equals 0, then x cubed equal y cubed. So, right? And it's symmetric trivially because it's an absolute value. So the absolute value of x cubed minus y cubed is the same as the absolute value of y cubed minus x cubed. And the triangle inequality is also trivial because we have what we call the triangle inequality for the absolute value. We can write x cubed minus z cubed, sorry, this is z cubed here. X cubed minus z cubed, which is the distance between x and z, rho of xz. I add and subtract y cubed. And by the usual triangle inequality for the absolute value, so the absolute value of the sum is less than the sum of the absolute values. Okay, and that's it. So rho of xz is less or equal than rho of xy plus rho of yz. Okay. Now observe that if you had taken x squared minus y squared, then this would not be a distance according to our definition. Why? Try to think, pause the video and try to think what is wrong, which property is not satisfied among these four properties. The first property is satisfied. The second property is not satisfied because if x squared minus y squared is 0, then x squared equal y squared. But if x squared equal y squared, we cannot conclude that x equal y because it's possible that x equal to minus y. So the second property is not satisfied. However, the third and fourth properties are also satisfied. Okay? Less trivial example, I take gamma of xy to be the minimum between 1 and the absolute value of x minus y for xy real numbers. And I claim that this is a distance in R according to our definition of a distance. Okay, it's not the usual distance, but it's a distance. So why this is true? Okay, we have to observe something important, that we can rewrite gamma of xy as, so gamma of xy is either 1 if absolute value of x minus 1 is bigger or equal than 1 because it's the minimum. If x minus y is bigger or equal than 1, then the minimum, the smallest between these two numbers is 1. If x minus y is less or equal than 1, then the minimum is x minus y in absolute value. So this is the same thing. So we can write as either as the minimum or as in this form. Okay, this is what we have to observe. And the second thing is that gamma is always less than 1 because it's the minimum, right? The minimum between two numbers is less or equal than both. So gamma is always less or equal than 1 and less or equal than absolute x minus y, no matter what are x minus y. Okay, so gamma is always bounded by 1. And I will use these properties, these observations in the proof that this is a distance. Okay, first property, the absolute value is bigger or equal than 0, and 1 is bigger or equal than 0, so strictly bigger than 0. So the minimum is bigger or equal than 0, right? It could be 0. It's 0 precisely when this is 0. Okay. So here maybe it's better to split the equivalence into two parts. if x equal y, so x equal y implies gamma xy equals 0 and conversely. So suppose first that x equal y, then the absolute value of the difference is 0. And so the gamma, by definition, is the minimum between 1 and 0, which is 0. Okay? And conversely, if gamma of x and y is 0, gamma is either 1 or absolute x minus y. But it cannot be equal to 1 because it's equal to 0. Therefore, it's necessarily equal to x minus y in absolute value. Right? But it's 0, so absolute value of x minus y is 0, and therefore x equal y. Okay, so almost trivial. But we have to write it. Okay, in the exam, when I ask you to prove that something is a distance, then you have to proceed methodically and check these 4 properties. Now, of course, in some texts, you will not find condition 1, which is non-negativity, because they write that the distance is a function from x times x into 0 infinity. Okay, but this is, I find this way of including condition 1 more pedagogical, because a distance should be non-negative. Okay. Symmetry is also trivial. So gamma of y and x is the minimum. So I go back to the definition, but y minus x in absolute value is the same as x minus y in absolute value, which is, so symmetry is trivial. Now, the triangle inequality is a little bit less trivial. So we have to distinguish between 2 cases. If I take now 3 real numbers, x, y, z, I want to prove that gamma of xz is less or equal than gamma of xy plus gamma of yz. So there are 2 cases. First case, one of these 2 numbers, y minus x minus y in absolute value and y minus z, one of them, maybe both, but one of them is at least 1. Okay? What happens in this case? I go back to the definition. If x minus y in absolute value is less or equal than 1, then the minimum between these 2 is 1. So gamma of xy is 1. If the second alternative happens, so if y minus z is an absolute value is bigger or equal than none, then gamma of y and z equal to 1, okay, because the minimum is 1. And what happens? Therefore, the sum of gamma xy and gamma yz is at least 1, because if this is 1, this is non-negative. So 1 plus something non-negative is at least 1, and vice versa. So if one of these 2 is 1, then the sum is bigger or equal than 1, because both are non-negative. But as we observed, gamma of xz is at most 1. Therefore, we are done. So gamma of xz is less than 1 or equal, which is less than the sum. So gamma xz is less than the sum of these 2. The alternative is that both, the negation of this case is that both are less than 1. Okay? Because this is not A or B, which is not A and not B. Okay? So both are now less than 1. In this case, gamma of xy is the minimum, which is absolute of x minus y, by definition of gamma. And now observe that here we have and, not or. And gamma of yz is exactly equal to y minus z in absolute value. And now we are almost done, because now gamma of xz, as you observed before, gamma of xz is always less than absolute value of x minus z, because it's the minimum of between this and 1. And now I apply the triangle inequality to the usual absolute value, okay? Because I can add and subtract y, as we did before. So this identity you probably know from high school. This is known as the triangle inequality for the absolute value. And now we just replace. This is equal to gamma xy, and this is equal to gamma yz, and we are done. We have the triangle inequality in this case. Okay, so we checked the 4 properties of a distance. And more generally, if we have a metric space xd, and we set d bar of xy to be the minimum between 1 and dxy, then d bar would be a distance on x. So same proof, just replace absolute value by d. Okay, and use the triangle inequality for d. Okay, this example is important, as we shall see later, because in section 3 we shall prove that in some sense d and d bar are equivalent. But D bar has the additional property that it's bounded by 1 from above, whereas D need not be bounded. Okay? So we shall use this fact later. So if you want, try to write the proof of this example for, or this is just copy and paste this, but replace absolute value by D. Okay? So I advise you to do this small exercise to test your understanding. Okay, so check that D bar is a distance according to our definition of a distance. Okay, by the way, if you find this video very lengthy, you can stop it from time to time, do the exercises, and see it later, continue it later. Okay, fifth example, less trivial. I consider the set of all continuous functions defined on an interval AB of real numbers. So it's a function from an interval of R into R. Okay, and I assume that these functions are continuous. So I suppose that you know something about continuity from first year. So now my space is not a space of numbers, it's a space of functions. Okay, so a point in X is not a number or a couple of numbers or a triple of numbers. This is now a function. Okay, and for any two functions f and g in this set, for any two elements in X, which are, so if f and g are elements of X, they are continuous functions from AB to R. So I set dfg to be the supremum, or the maximum actually, between f of x minus u of x in absolute value. We know that we can put max instead of sup here because we know that a continuous function has a minimum and maximum value on a compact interval. Okay, so this is the biggest distance, if you like, between f of x and g of x. Okay, I claim that D is a distance on this space. Okay, let us prove this, but first observe that by definition, dfg, because it's a maximum, is bigger or equal than f of x minus g of x for any x. You can put here f of t minus g of t is less than dfg for every t between a and b. So this is by definition. Okay. Now, of course, because since the absolute value is non-negative, the maximum of all these numbers is also non-negative. So the distance is non-negative. Trivial. Okay. Now let us see when it is exactly equal to 0. Suppose first that f equal g, then f of x equal to g of x for every x. And so this is just 0. So the supremum of 0 is 0. Right? So the distance would be 0. And conversely, if the distance between two functions f and g is 0, then so first the absolute value is non-negative, so it's bigger or equal than 0, and it's less than the distance between f and g as you observed here. So this quantity here for any x is between 0 and 0, so it's 0. Therefore, f of x equal to g of x for every x, and therefore it's the same function. Okay, because f and g have the same domain, the same target set, and they coincide at each point, so they are equal as functions. Symmetry is trivial because absolute value of g minus f is the same as absolute value of f minus g. So here there's an error, that's just dfg, not point. Triangle inequality, not difficult, but a little bit. Usually the triangle inequality is less trivial than the other properties to check. So I apply first the triangle inequality for the usual absolute value. Now I have, if I fix x in AB, then f of x, and take three functions, f, g, h, then f of x minus h of x is less than the sum, f of x minus g of x in absolute value plus g of x minus h of x in absolute value. Okay? So this is the usual triangle inequality of high school that for numbers, for real numbers. Now, as you observed, this is less or equal than df, so there should be an equal, less or equal here, sorry for the mistake. So this term is less or equal than dfg, as you observed here, and the second term is less than the distance between g and h. So dfg plus dgh is an upper bound, and this is true for every x. So this constant here now doesn't depend on x, is an upper bound of f of x minus h of x. Therefore, it is bigger or equal than the supremum, because the supremum is the smallest upper bound. So we get the distance between f and h, which is by definition the supremum, is less or equal than dfg plus dgh. Okay? So this concludes the example 5. Okay? By the way, this distance is called the distance of uniform convergence. Why? Because convergence, we shall talk about convergence later, but convergence in this distance is equivalent to uniform convergence of functions. Okay, so we shall see that later. Okay, as an exercise, take a equals 0, b equal pi over 2, and f to be the identity, and g to be the sine function. Compute the distance between f and g. Not difficult. So I suggest that you pause the video and solve it, just to get a feeling of what it is. Actually, you can draw the graph of x and the graph of sine and see where they meet and see the maximum distance between the two, between the graphs, actually. A less trivial example, example 6, we take the same set, the space of continuous functions from AB to R, CAB, and now define another distance, but I use the same symbol D, but you can use another symbol. You can put here D1 if you like. But now this is a different kind. The formula is different. Now, instead of taking the supremum of f of x minus g of x, we take the integral of the difference, which means what? It means this is the area of the part between the graphs in absolute value. Okay? So maybe you can draw a figure. If this is f, this is g, then you should, okay, so this is the area between the graphs of the two functions. Okay, now, and this is a distance. Why? First property, trivial, non-negative, because the absolute value is non-negative. So when we integrate, we know that integration conserves inequalities, so we get something non-negative. And now we split into two parts. If f equal to g, then in absolute value, f of x minus u of x, absolute value here, is 0. So when we integrate, we get 0, because the integral of 0 is 0. And conversely, if the distance between f of g, between f and g is 0, then the integral is 0. Now we have to use a non-trivial result from integration, which tells me that if I have a continuous function on an interval AB, which has a constant sign, for example, non-negative or non-positive, and if the integral is 0, then necessarily h is 0, is identically 0. Okay, and this is what we have here. F and G are continuous. This is where I use continuity, actually. If f and g are continuous, then their difference is continuous, and therefore the difference of the absolute value of their difference is 0. So what is inside here is a continuous function, which is non-negative, and therefore it's 0. So f of x equal to g of x for every x, and therefore f equal to g. So this is the only non-trivial point here. Okay. Symmetry is clear, because absolute value of g minus f same as absolute value f minus g. Triangle inequality, almost trivial. We use the triangle inequality for absolute value as usual. So absolute value of f of x minus h of x less than the sum. And I integrate. We know that integration conserves inequalities. So the integral of this first term is less or equal than the integral of the sum. But the integral of the sum is the sum of the integrals. So it's equal to the integral of this plus the integral of this. And we get precisely on the left-hand side dfh, and on the right-hand side dfg plus dgh. Okay. And as an exercise, take a equals 0, b equal pi over 2, the same as before in the previous exercise, the identity and the sine function, and compute the distance between f and g for this distance and compare with the previous exercise. It's not this. It's not the same result actually, because it's a different distance. Okay, last example, the discrete distance on any set, non-empty, of course. So the discrete distance on an arbitrary set X is just a function of two variables that takes only two values, 0 and 1. Okay, it takes the value 0 only if X equal Y, and takes the value 1 in the other cases. And so this is a distance according to our definition. Okay, first three properties should be clear for you. You can do it mentally. It's 0 or 1, so it's bigger or equal than 0. Symmetry is clear because X equal Y means Y equal X. X different from Y, Y different from X. Symmetry is clear. It's 0 precisely when X equal Y. Right? Now, less trivial is the triangle inequality. So consider three elements X, Y, Z in the set X. So here, once again, you have to distinguish between two cases. So if X equals Z, it's clear because then the distance between X and Z is 0. And the distance between X and Y is bigger or equal than 0. So it's at least 0. And the distance between Y and Z is at least 0. So the sum is at least 0. So this is equal to 0, and the sum is at most at least 0. So we have the triangle inequality. Now, the second case, the alternative assumption is that X is different from Z. If X is different from Z, then either Y is different from X or Y is different from Z. Why? By contraposition. Because if Y equal, what is the negation of this assumption here, this sentence? Y different from X or Y different from Z. The negation of this is Y equal to X and Y equal to Z. By transitivity of equality, then X would be equal to Z, but I have X different from Z. Okay, and in this case, what happens? If Y is different from X, then the distance between X and Y is precisely 1, right? And if the second case happened, if Y is different from Z, then the distance between I and Z equal to 1. And therefore, we are done. The distance between X and Z is 1 because the X is different from Z. And now, if one of these two guys is 1, the sum is bigger or equal than 1 because they are non-negative. We encountered this idea before. Okay, if this is equal to 1, since this is non-negative, the sum is bigger or equal than 1, and vice versa. So the distance between X and Z is 1, and the sum is bigger or equal than 1, so we have the triangle inequality in this case. Okay, so this concludes the examples. You may stop the video now and take a break if you like, before we move to something else. And when you are done, we may continue. Now, we would like to revisit some distances on Rn, on n-dimensional space, that you may have encountered in first year. Of course, n is a positive integer, so it's at least 1. Recall that R to the n is by definition the set of n tuples, okay, finite sequences, x1, x2, xn. So x1, x2, xn are the coordinates of this point. Now, so otherwise stated, Rn is what we call the Cartesian product of n copies of R. Okay. Now, the origin of Rn is just the vector, if you like, or the n tuple 0, 0, 0. So just write 0 instead of n zeros. Okay. Now, what is a norm? You may probably have heard of norms on Rn, or on a vector space more generally, but let us concentrate on Rn because you will study normed vector spaces in the next semester. So here we just restrict ourselves to R to the n, which is the simplest example of a vector space. A norm is a way to measure the length of the vector x1, xn. So in some sense, it's a generalization of the absolute value of a real number. Okay, so a norm in general on Rn is a number. It should be non-negative. It's a real number denoted in this way, two vertical lines, norm of x. So first property, non-negative. It's 0 precisely when the vector is 0. when I multiply by lambda by a scalar, this is what you call homogeneity. So when you multiply the norm of a multiple of x is the multiple of the norm of x, but in absolute value, because lambda could be negative. Okay, and we have the triangle inequality as well. Okay, this is the definition of a norm. Now, I cannot define this on any set like I did with the concept of a distance, because I need the concept, I need two things. I need addition to be defined, but addition is not necessarily defined on any set. And I need the concept of a multiplication by a scalar. In general, if you recall from first year, a set equipped with these two operations is called a vector space. Okay, so this definition is very general. On Rn now, of course, I have the concept of sum of two vectors, just component by component. I have the concept of a multiple of a vector, just multiply each component by the same number. Okay, so this is the definition of a norm. And you may have encountered such norms on Rn before. We have first the Euclidean norm, Pythagoras theorem. This is what we call the Euclidean norms, the sum of the square of the components raised to the power 1/2, so radical of this. So this is what we call the Euclidean norm on Rn. Okay, this is a generalization of the Euclidean norm on R2 with which we started in the beginning. So we usually write subscript 2 here in order to distinguish between other norms. So other familiar norms are the infinity or the supremum norm. So the infinity norm is just the maximum, the biggest between the components in absolute value. And it's not difficult. Maybe you proved it last year. This norm infinity satisfies the fourth property of a norm. Okay, so non-negative, it's 0 when all components are 0. When I multiply by lambda, I can put lambda outside in absolute value, triangle inequality, and so on. So I will not repeat the proof here. You can do it as an exercise if you like. Just check the three properties of the norm. Another familiar norm is the one norm. So just take the sum of the components in absolute value. This is the one norm. So we have now three norms: the one norm, the infinity norm, and the Euclidean norm. And more generally, so here again, maybe you did it last year. It also satisfies the four properties of a norm, same thing. And more generally, we have the P norm. The P norm is a generalization of the one norm and the two norm. Instead of taking P equal 1 or 2, you can take any P bigger or equal than 1. So it could be, for example, 3 or 4. So take the sum of the pth power of each component in absolute value and raise everything to the power 1 over P. So the two norm is a particular example. The Euclidean norm is a particular example of this. The one norm, just take P equal 1. So we have a collection of norms. Now, the first three properties of a norm can be easily checked. Okay, non-negativity, symmetry, etc. Multiplication by homogeneity. It's 0 when all components are this trivial. But the triangle inequality is not trivial to prove. Okay, maybe you did it last year. I don't know, but we shall not use it in this course. Okay, so the triangle inequality in this case follows from another important inequality in mathematics known as Hölder's inequality. Okay, so we have now a collection together. So we have a collection of norms indexed by P, and you have the infinity norm, which is actually a limiting case of this, because you can prove that when P tends to infinity, this term tends to this term. It's not difficult to. So infinity is an extreme limiting case. Okay, and now what is the relation between norms and distances? It's very easy. If I have, of course, and I should note that when n equal 1, all these norms are the same, because you just have one component. Now, the connection is very simple. If we have a norm on Rn, any norm you like, one of these, for example, or maybe you can invent others. So if you have a norm on Rn and put dxy equal the norm of the difference between x and y, then we get a distance. So d is a distance in this case. Check that, write it as an exercise. So non-negativity clear because it's a norm. It's 0 if only if the difference is 0. So when x equal y, And symmetry, of course, is clear because norm of x minus y is norm of y minus x by property 2, by homogeneity. Okay? And triangle inequality for D follows from the triangle inequality for the norm. Okay? So, okay, so this concludes this subsection on norms on Rn. Now I want to talk about balls in a metric space. We have two kinds of balls, open balls and closed balls. If you have a metric space XD, then the ball of center x and radius r, denoted by bxr, is by definition, as in the familiar case of a ball in three-dimensional space, is the set of points y whose distance to the center is less than the radius. Okay, so this is a generalization of the concept of geometric ball in R3. And we have the notion of closed ball. So instead of strictly less than the radius, we include the sphere, we include the boundary. Oh, all right. I didn't talk about boundaries yet, but so the closed ball is the set of points. So the closed ball of center x and radius r is the set of points y whose distance to the center is at most r, so less or equal. So of course the open ball is contained in the closed ball. And remark, if we sometimes we may put more than one distance on a set. So we have two concepts of balls. In order to distinguish these two balls, so if I have, so we write, if you have a distance d, the open ball of center x and radius r can be denoted by b sub d of xr in order to emphasize that this is the ball with respect to the distance d. And similarly for the corresponding closed ball, bd prime xr. Therefore, if we have two distances, for example, d and d prime, or d1 and d2, then we have two balls, bd1 xr, bd2 xr, bd prime, bd1 prime, bd2 prime. Okay, so we will need this later because when we want to compare distances, when we will talk about topologically equivalent distances, we need to distinguish between two kinds of balls. Okay, and now as usual, I will give a series of examples. First example, just take x equal r, the real line, with the usual distance. Okay, so the usual distance is dxy is absolute value of x minus y. What is the open ball of center A and radius r? As you may know, this is the open interval A minus r, A plus r. Why this is true? Because x belongs to this ball by definition if the distance from x to A to the center is less than r strictly, but the usual distance is just the absolute value. And now the absolute value is just x minus A or A minus x. So saying that the absolute value is less than r means that what is inside is between minus and r and r. So when I add A, I get that x is between A minus r and A plus r, and therefore we get that BAR is just the interval A minus r, A plus r. This is the ball in one dimension. We still call it a ball because we use the concept of a ball in a very general sense, not the usual geometric ball of R3. So this may be confusing if it is for the first time, but this happens always in mathematics. So when we introduce, when we give more meaning to, or a general meaning to a concept, a familiar concept, we broaden the applications. Okay, so an interval is a ball. Okay, but don't tell this to your small brother because he will be confused how an interval could be equal to a ball. Everything depends on the definitions. And similarly, the closed ball B prime AR with the usual distance is just the closed interval A minus R, A plus R, same thing. Now, if we equip R2 with the Euclidean norm, or the Euclidean distance, if you like, that just talk about, the open ball BAR is just the usual open disk. Now, a ball is a disk. Okay? Why this is true? Because a couple x1, x2 belong to this ball if the Euclidean distance is less than r, but the Euclidean distance is just, by definition, x1, first component minus first component, second component minus second component squared, of course, and then take the radical. And if this is less than r, this happens if and only if, when I square, I get x1 minus a1 squared plus x2 minus a2 squared. Of course, I can drop the absolute value if you like because it's a square. And what's that? This is the set. This is a disk actually, right? So you can picture this is a disk of center a1, a2, and radius r. But note that I put it in a dashed line because I'm excluding the boundary. So the open ball in this case is just the full open disk, okay, without the boundary. So right. So here a ball in R2 with respect to the Euclidean distance is just a disk. It's what we call a disk. So here we distinguish between disk and circle, as you know, because the disk is what is inside, and the circle is just the boundary. Okay, and for the closed disk, same thing, but we include the boundary, we include the circle. Same thing. Okay. Now, in R3 with the Euclidean norm, as you know, we get the familiar geometry. Okay, so a ball in R3 with the Euclidean norm is just the familiar usual geometric open ball of center A and radius R that you can picture, you can draw if you like. Okay, so here the two notions coincide. A ball is a ball. Okay. Now let's trivial example, and same thing for the closed ball. Same remark. Okay, so the closed ball contains the boundary. The open ball does not contain the boundary. So here the sphere is contained in the closed ball, but does not meet the open ball. Okay, let's trivial example. Fourth example. What if I take the infinity norm? Okay, in R2. What is left? Just to simplify, instead of taking BAR, just take B01. This so the ball of center 0 and the radius 1. I claim that this ball now is a square, is a full square, actually, without the boundary, of vertices -1, -1, 1, -1, 1, 1, and -1, 1. And I will draw it in a moment. Why this is so? So just by equivalence, so x1, x2 belongs to this ball. So because we are working in R2, so it's a couple. So a couple of numbers x1, x2 belong to this ball. I go back to the definition. If the distance between x1, x2 and the center, which is 0, 0, is less than 1, okay? But what is the infinity norm? So the infinity norm of x1, x2 minus 0, 0 is just the maximum between x1 minus 0 in absolute value and x2 minus 0. So this is just the norm of the difference. So this point belongs to the ball if the maximum is less than 1, which is equivalent to saying that the maximum in absolute value is less than 1. And this happens if and only if both x1 and x2 in absolute value are less than 1. So we have a complete equivalence here. And what does it mean? This happens if and only if x1 is between -1 and 1 and x2. So first component is between -1 and 1, and same thing for the second component. And I get, so this is the boundary of the square actually between, so this is the, this is -1, 1, -1, -1, 1, -1, 1, 1, and -1, 1. So these are the vertices. But here x1 can be anywhere here, and x2 can be anywhere here. So the couples is just the square, the full square, okay? But you don't include the boundary because x1 is never equal to 1 or -1, and same for x2. So this is the full open square. So here we have something that may look strange. A ball for the infinity norm is a square, is a full square. Here we have to distinguish between full square and square, because usually square is the boundary. Okay, so a ball is a square. So don't be misled by the use of the vocabulary, because here for us the concept of a ball depends on the notion of a distance. Okay, when we change the distance, the ball changes. Okay, so this is the open ball of center 0 and radius 1. And more generally, you can see that the ball of center A and radius R is also a square, but the center would be A and the radius, the side of the square actually would be 2R, right? Because here we have the length is 2. Okay. And similarly for the closed ball, the closed ball is just the full closed surface, so we include the boundary actually. Okay, and fifth example, what if you take the one norm in R2? Okay, so the distance here between 2 points x1, x2, and y1, y2 is just absolute value of difference between first components and second components. And now this is also a square, but it's a rotated square. How do you know that? Okay, so first, observe that x1, x2 belong to this ball. What does it mean? It means that the distance between x1, x2, and 0, 0 in the one norm, which is just x1 minus 0 plus x2 minus 0. So a couple x1, x2 belong to this strange ball if the sum of the components in absolute value is less than 1. Okay, now let us try to understand what's this geometrically. Okay, we have, in order to understand it, we have to distinguish between 4 cases because we have absolute values here. So we have to if we want to remove the absolute values, we have to distinguish between the case x1 non-negative, x2 non-negative. One of them is negative. Okay, both are non-negative, both are non-positive. One of them, so you see, so we split the R2 into 4 regions, into quadrants. First quadrant, second quadrant, third quadrant, and fourth quadrant. So in the first quadrant, both components are non-negative. And in this case, I can remove the absolute value. So in this case, we have x1 plus x2 is less than 1. Now, otherwise stated, x2 is less than 1 minus x1. So geometrically, what does it mean? It means that this is the part below the line of equation 1 minus x1. But we need to intersect it with the first quadrant. So we get actually, so we are here in the first quadrant, x1 positive, non-negative, x2 non-negative, but we are below this line of equation x2 equal 1 minus x1, which joins 0, 1 to 1, 0. Okay, we are below, but we should be in the first quadrant as well. So we get this triangle. Okay, and we continue for so this is the first quadrant, second quadrant, third quadrant, fourth quadrant. So second quadrant, the first component is non-negative, the second component is non-positive. And now, in this case, the absolute value of x2 is minus x2. So we get x1 minus x2 less than 1, or equivalently, x2 is bigger than x1 minus 1. So it's the part above the line of equation x2 equal x1 minus 1, and which this is parallel to the first bisector and passes through the point 1, 0. So we are above this line, but we should be in the second quadrant, and therefore we get this triangle. And you guessed what's next. Third quadrant, both are negative. So the absolute value of x1 is minus x1, because now minus x1 is positive. And absolute value of x2 is minus x2, so you get minus x1 minus x2 is less than 1, or x2 is bigger than minus x1 minus 1. So we are now above the line of equation minus x1 minus 1, which is parallel to the second bisector. So we are above, so we are in this region here. And finally, the fourth quadrant, first component non-negative, second component non-positive, and therefore the absolute value of x1 is minus x1, absolute value of x2 is x2. Therefore, we are below the line of equation x2 equal x1 minus 1. So we are here. Okay, so we have this triangle, and therefore we have to now put everything together. And when we put this, we get the interior of this rotated square. Okay, without the boundary. So here, the ball of center 0 and radius 1 with respect to the one norm or one distance, if you like, it's a rotated square. And of course, same thing for the closed ball. We just have to include the boundary. So we have everything now. Okay, so here a ball is a rotated square. Okay, because meaning of ball is very broad now. Okay, So it includes a lot of familiar things. It includes intervals, squares, rotated squares, geometric balls, and something that you cannot picture. Okay, and last example, the discrete distance on an arbitrary set X. What is the ball of center A? Any A. A is arbitrary. The ball of center A and radius 1, we claim that it's the singleton A, so it's just the center. And the closed ball of center A and radius 1 is the whole space. So this is really an extreme, unfamiliar case. How a ball could be a singleton? Yes, because our definition of a ball is very general. Okay, so this seems counterintuitive. But why this is so? How to prove that this is equal to A? Of course, double inclusion, or just equivalence. So a point X belongs to this ball of center A and radius 1, if and only if the distance, so it's the center between X and the center, is less than 1. But the distance is either 1 or 0. Since it's not equal to 1, then necessarily it's 0. Right? This is not true for every distance. This is just very specific to the discrete distance. So the distance is 0 happens when X equals A. So an element is here if and only if it's here. Okay, so the open ball of center A and radius 1 is just reduced to the center of the ball. And for the second one, why the closed ball is the other extreme? How do I prove that? Double inclusion. Of course, B prime A1 by definition is an X, because X is the universe in which we live. So I have to prove that any element in X is here. But if X is an arbitrary element of the capital of the space X, then the distance, since it's either 0 or 1, it is at most 1. So it's less or equal than 1. And this means that X belongs to the closed ball of center A and radius 1. And therefore, we have this inclusion. Double inclusion means an equality. And that's it. So we may use this example as a source for counterexamples in metric spaces. Okay. So this concludes this video. We covered section 1.1. Next video we'll start actually by section 1.2. We'll split it into several videos because it's a little bit lengthy. Okay, so thank you for your attention and see you soon. And one more time, study regularly. And I have to tell you just something, that the lecture notes of this course are available on my website, but I'm updating them because I'm changing from last year. So it will take some time, but the lecture notes are sometimes sketchy, so the video lectures are much more detailed actually, because in class I usually write all the details. Okay, so you may use both actually to study. So thank you for your attention and see you soon.